Visual communication is one of three types of communications us humans have developed over many years. The three ones that I'm talking about here are verbal communication, nonverbal, and visual, the one which is the topic of this entire class. Verbal communication is very likely what you're thinking about. It's exactly what I'm doing right now, talking to you with words. And it can be words, it can be sounds, anything that comes out of your mouth. Now, nonverbal, on the other hand, is anything that can be communicated with your body without words. So maybe your emotions, your facial expressions, your posture, anything that doesn't require you to talk. Now, what is visual communication? Well, it's the transmission of information and ideas using symbols and imagery. That can be signs, film, typography, graphic design, photo, ads, blueprints, video games, drawings, paintings, TV. Good visual communication is communicating a message in the most effective way possible. Nowadays, visual communication is very likely the most important ways of communicating because it crosses languages, it crosses culture, and essentially good visual communication is the ability to communicate a message in the most effective way possible with the greatest level of understanding as a result. Visual communication is especially important for artists because it is our main way to communicate. We communicate with our work, with our art, the way this art is perceived, the way it's received, the way it's appreciated, all has to do with how we're able to communicate using visual communication. So I'm really excited about this class. You have a lot to cover, so let's get started. The first thing I want to talk about in this first chapter is what is visual literacy. So seeing is a really complex process that involves obviously the mind and the eyes of the viewer. We learn pictures before we learn the words that are attached to them. We learn the alphabet as children, for example, by attaching each letter to a picture, A for apple, and then in school we learn to read and write, but we are never taught how to read images. Today, we live in a visually mediated society. Pictures fill up our media, from magazines to posters to computer to the internet to everything that we see. There's so much visual content. Our world now is being more and more understood or potentially misunderstood by the images that we see. Visual literacy is our ability to interpret, negotiate, and make meaning from information presented in the form of an image. Essentially, it's extending the meaning of literacy, which usually refers to the interpretation of a written or printed text. The idea here is that since we are taught in school to learn and to read text, it's now important, especially now since we are exposed to so much images, to learn how to read those images in a very similar way as reading text. So to be able to look at an image and understand more than just what is on the surface and be able to be critical about it. That term, visual literacy, is actually credited to a man called John Debus, who's the co-founder of the International Visual Literacy Association. So in 1969, he offered a definition of the concept, which goes like this. Visual literacy refers to a group of vision competencies a human being can develop by seeing. The development of these competencies is fundamental to normal human learning. When developed, they enable a visually literate person to discriminate and interpret the visible actions, objects, and/or symbols, natural or man-made, that he encounters in his environment. Through the appreciative use of these competencies, he is able to comprehend and enjoy the masterworks of visual communications. So, visual literacy is all about knowing how vision works, how to interpret images, and how to put them into context, to be aware of manipulation, and the fact that we all hold highly personal views of the world. Knowledge of the creation process for images is also quite important. It's important because we need to look carefully at images, critique and analyze the messages we see objectively. It's also important because we have to be careful to be aware of mindsets and check our own biases. And it's important because we need to discriminate fact from fiction, avoid media manipulation from marketing, political, and special interest groups. Today, we have a very interesting phenomenon happening, which is pervasive visual images. So, if you want to see someone do a painting from scratch right on video on YouTube, well, it's just a click away. You can easily see this. What's even crazier is that everything you decide to upload online or just store on the cloud or upload to a hard drive has good chances to stick around forever. And it's no longer just the images that professionals post that become part of the culture. Today, everyone has the ability to instantly share images via, just social networks. So as opposed to before, where only a few samples were ever kept and maintained and discovered, nowadays, everybody that creates something and that actually uploads it on the internet will likely have this one thing be permanently there. The amount of content that is uploaded on YouTube, for example, or Snapchat, or Instagram, Twitter, is just mind-boggling right now. There's so much content everywhere. In 2012, a study by ROI Research found that when users engage with friends on social media sites, it's the pictures that they took that are most enjoyed. 44% of respondents are more likely to engage with brands if they post pictures than any other media. And pictures have become one of our default modes of sorting and understanding the vast amount of information we're exposed to every day. According to educational psychologist Jerome Bruner of New York University, studies show that we remember just 10% of what we hear, 30% of what we read, but 80% of what we see and do. We hear of an important news and event, we rush to see the images on our mobile device, computer, and televisions. And the way visual content affect our memory is also very interesting. Just like you will likely remember a lot of things when you hear a song that you associated with a very particular memory from years prior. The same applies to images, and in this case, we're bombarded with images on a daily basis. So this is creating a really interesting shift in the way that our memory is getting structured compared to before. And just like music, artworks have such a powerful impact on memory that if you see a piece and you were in a particular state of mind at the time you saw it, and you see that same piece of work multiple years later, everything will come back just the same way as with music. But all of this doesn't really make much sense until we actually understand how we see, which is what we're going to explore in the next chapter. The way we see seems to be the first natural topic to cover when it comes to visual communication. After all, us as humans see the world very differently than other species. And not only that, but each of us sees the world differently. When it comes to colors, for example, there are some tribes that will only be able to identify a certain number of colors, and other cultures will be able to discern many more. This, regardless of the fact that our eyes see exactly the same thing. This all has to do with our visual process, which can vary greatly between one individual and another. Perception plays a massive role in our ability to memorize and analyze what we see. Perception is the process by which we select, organize, and interpret sensory stimulations into a meaningful and coherent picture of the world. This perception of or visual analysis of the things that we see is critical to understand the image in the world, and the more observant we become, the more we see, learn, and remember, and the more we're able to draw in the future. So, for example, memory alone would not allow you to become a good artist. You would need memory and the understanding of what you're actually looking at to be able to memorize it properly and store it in a way that you can access it in the future and use it for artistic work. Think of it as a good librarian versus a bad one. The good one will be able to organize the library very effectively so that customers can find exactly what they're looking for very easily. And the bad one won't be able to organize much at all, creating a lot of confusion for the customers and really bad experience. Now, unfortunately, even though we might be able to perceive a lot of different information and a lot of different images, at best we're still only able to retain a very small portion of everything we see. But hopefully, by understanding what happens in the background of our brain, we should be able to increase that portion a little bit. When it comes to the type of visual images that the brain can understand and process, there's only really three different groups. The first is mental images. Those you experience from inside your mind, so your thoughts, your dreams, fantasies. For example, how you think about an apple. The image you have in your mind is a mental image. There's another one, which is without media intervention. So real objects you view in a live experience. For example, look at an object that is in front of you right now. That object right in front of you is right there and is not mediated in any way. And then the third way is mediated images. So those are seen through some type of print, screen, movie, TV, computer, tablet, cell phone, whatever it is. So for example, if you're listening to this on your computer or your tablet right now, the images that you see are mediated by the device you are using to view them. So you might have guessed it, but the type of images that are most valuable for us artists are mental images. The clearer they are, and the more detail we can recall when processing those types of images, the better equipped we are when it comes to transferring it on canvas and actually creating something from imagination. Now, this all has to do with memory, of course. We can't fetch or recall something we haven't stored properly. But like I briefly mentioned at the beginning, images alone do not get stored in memory unless there's a word to attach to that image as well, at least in most cases, or it won't get stored well. If I bring back the example of those tribes seeing only very limited number of colors, there's also other tribes that will be able to discern a really incredible number of variations of greens, for example, way more than you and I can do. And by that, I mean way, way more. And this is only due to the fact that they have distinct words for all those different shades of green, allowing them to efficiently store those very slight nuances in colors, associate a word with them, and store them in their memory. But obviously, words alone are not the only criteria when it comes to, storing images in memory. Emotions are also quite effective for that. Emotional responses can make images much more memorable. Without bringing up any example, I'm sure you can think of a number of images right now that you can vividly remember having seen a long time ago for the simple fact that they made you really, really angry or disgusted. Another significant way we store images in our visual memory is through various associations or links between past images. For example, if you've had a period in the past where you were drawing a lot of birds, for example, seeing a new bird drawing should be enough of a link to help you remember that image in the future more than, say, a similarly made mouse drawing. Images can also have literal meaning and symbolic meanings. So one image might actually have both. All messages, verbal and visual, have literal and symbolic components. Literal means that you understand what you're looking at. For example, you see an apple and you think of an apple. While a symbolic meaning is when you see an object or images and it means that you may perceive a deeper or emotional connection there, something else than the actual just literal thing that you're looking at. For example, when you see an apple, perhaps you think of the apple pie that your mother makes, or you may think of the apple in the Garden of Eden, and you might also be thinking of just Apple products like the company Apple. And then similarly, if a person flies a flag outside of her or his house, the symbolic meaning is that he or she is patriotic. At least that's what most people would think. Before you can store anything as memory, however, you first have to see it and see it clearly. So sensing plus selecting plus perceiving equals seeing. The first stage, sensing. It's essentially letting enough light to the eye so that you can see objects. So pretty basic. Stage 2, selecting. It's isolating a particular part or a scene or event, and that requires light, eye focus, and a high level of brain functions, a conscious intellectual act. So selecting starts the process of classification. We may ask ourselves if this thing is familiar, dangerous, pleasant, meaningful, meaningless. Then the stage 3 is perceiving. It occurs when we make a sense out of what you have selected to pay attention to. So before we remember it and store it, we consider its meaning. It's more than an observation. It's an observation that has been viewed and considered and sorted. The more you know, the more you perceive. For example, a professional artist that's been studying anatomy extensively, you'll be able to be aware of all the different muscles, the way they look in certain pose, the way they deform, the way they stretch, if a muscle in comparison to another muscle is too big or too small. And this is all stuff that a novice would never be able to perceive. So yeah, you can think of this as a bundle of knowledge. The professional has a much larger bundle of knowledge than a novice does. As we move through the class, your bundle of knowledge and visual communication will increase. You will have more examples to draw on to perceive images in deeper ways. So the more you know, the more you sense. And the more you sense, the more you select. And the more you select, the more you perceive. And the more you perceive, the more you remember. And the more you remember, the more you learn. And the more you learn, the more you know. So what does it take to be a better perceiver? Be curious, ask questions. Good sensing and perceiving takes a questioning mind, one that doesn't just accept everything as it appears to be on the surface. So a bank of knowledge is important. Things you have learned and your experiences can help you see the forest for the trees. As you analyze visual images, you take a careful look, think, and add to your knowledge. Knowing about all of this definitely helps a lot when it comes to the way you'll see things around you from now on, but to really store the extra information deep in your memory, you have to make a conscious decision at almost every moment of the day to really analyze what you're looking at instead of simply glancing over things. And I'm not talking about images only here. I'm talking about actually everything that you're actually looking at. So when you look at your hands, don't take it for what it is. Actually look at the hand and look at where the pores are on your hands and where they're not. Look at the different folds and how big they are, how deep they are in comparison to maybe other parts of your body. Maybe look at how the color of the tip of your finger is in comparison to your knuckles, or how shiny the skin is on top of your hand in comparison to your nails. It can be anything. I'm just giving random examples here, but you can do the same process for everything that you look at. It doesn't actually have to take much longer, and it actually doesn't, but it definitely takes you to make a conscious decision to spend that extra time looking at what you see. And this is something that does not come easy, and definitely as an artist, it's something that you have to make into a habit. There's no going around that. How we see all begins with light, however. To understand images, we first must understand a bit about it. Humans have always been curious about the nature of light. So, sunsets, sunrises. Why are we always so impressed by that? So drawn to those things. Just like fire, also lightning. Without light, we would see nothing. Our language is peppered with expressions that uses the word light, for example, like I've seen the light, or that won't see the light of day, or can you bring light to the subject? or I'm in the dark, or he's out like a light, or she's the light of my life, or that's light years away. It's just everywhere in our languages, and for a reason. It's just something that's really, really important to us as a species. But now that we're talking about it, what is light? A simple definition of light goes like this: the natural agent that stimulates sight and makes things visible. An electromagnetic radiation from about 390 to 740 nanometers in wavelength. The speed of light traveling in a vacuum is 186,282 miles per second, or 700 million miles per hour. The speed of sound in air is about 740 miles per hour, making the speed of light almost a million times faster. This is the reason why we see the lightning before the thunder, for example. The current theory for light was theorized in the year 1900 by Max Planck, and it is essentially saying that the light is made out of photons, and photons are both particle and waves at the same time. And then Sir William Herschel in the year 1800 discovered infrared radiation by projecting the colors of the visual spectrum through a prism. So I'm sure a lot of people have seen this before. It discovered that each color had its own temperature. He found that the temperatures varied beyond the visible colors and concluded that the light must have components that humans simply cannot see. The human eye only sees a small portion of the electromagnetic spectrum, and you can see that right here. As humans, we interpret different wavelengths of light as different colors. Violet has the shortest wavelength in the spectrum, then goes through blue, green, yellow, and red has the longest wavelength. What we see is an object's or image's reflected light. For example, we see orange as orange because an orange will absorb all the frequencies except orange, which it reflects back. So the same way we'll see, leaves green because the leaves will absorb all the colors except the green, which it will reflect back to our eyes. And then an object that appears white reflects all the colors of the visible light spectrum to the eyes. They all combine to form white. And then in the same way, the opposite, an object will appear black if it absorbs all the visible light frequencies, meaning that none of those frequencies is going to bounce back to our eye. And finally, a quick note about luminescence, which is a particular light source that artists will use quite often, at least I do. What it is essentially is the emission of light by a substance that is not resulting from heat. It's a form of cold body radiation. It can be caused by different chemical reactions, electrical energy, subatomic motions, or stress on a crystal. Some molecules become excited and go into a high energy state when light photons fall on them. Other compounds glow when light is taken away, but the general term to describe this is luminescence, the emission of light by a substance caused by physical or chemical means. Just like it's really important for artists to know how their tools work and how to handle a pen, how to properly use a pencil, and how to go about using something like Photoshop, another one of those essential tools that everybody has that we must understand if we are to create art is the human eye. I'm sure you're aware that we can easily be fooled by a number of visual illusions, and even though we might know for a fact that what we're looking at a particular point is wrong or not what it seems to be, our eyes will still fool us in seeing something completely different. For this reason, it's really important to understand how the eye actually functions so that perhaps we can use this knowledge to our benefit when creating art. I'm not going to go into too much details when it comes to the anatomy of the eye, but there are certain things that I really want to either refresh your memory with or teach you that things that are essential in how we see things, how we perceive colors, shapes, and in our ability to focus, just like your real camera can. So before we look at the different parts of the eyes, let's just take a quick look at how the eye works and what allows us to be able to see images. So first, light rays will enter the eye through the cornea, the pupil, and then the lens. It will then pass through the vitreous humor, a clear gel-like substance that fills the middle of the eye, and then the lights will finally land on the retina, a light-sensitive tissue lining the back of the eye. From there, the retina and its photoreceptors will send the information gathered to the optic nerve, which will then transmit it to the brain, where it will be able to translate it into visual images. Now, we're not going to look at every single part of the human eye because there are quite a few, but most of them are not really relevant for us artists anyways. However, there are some key parts of the eyes that I really want to take a look at. The first one would be the sclera. The sclera here is the first layer of the eyeball. It's a tough protective membrane, and it is essentially what most people will call the white of the eye. Now, the iris, right here, is a muscle that changes the size of the pupil, which is the black, the black center portion here of the eye. The muscle of the iris changes the pupil size from 2 to 8 millimeters, and it is what gives the eye their color. So the amount of melanin in the iris is what is going to dictate the color of your eyes. So eyes that have more melanin will be darker, so shades of brown and black, and will be also more resistant to the sunlight. The amount of light that comes in the iris or inside the eye will also depend based on if its muscles enlarge or contract the opening. The iris also shows emotion. So, for example, when you see something or someone that you really, really like, our iris tends to contract and enlarges the pupil. The iris is essentially the same thing as the diaphragm on a camera. Now, the pupil, right here, like we briefly looked at, is simply the dark opening in the center of the iris, in the center of the eye. This will be the same as the aperture on a camera. Now, sitting in front and essentially protecting everything that we've seen so far is the cornea. It's a tough, transparent window that bulges slightly in front of the center of the eye. It has 4 to 5 transparent layers that reduce the speed of light by about 25%, and then directs the light towards the center of the eye to aid with focus. About 70% of focus is from the cornea, and the lens will generally do the rest. The cornea has absolutely no blood vessels. And like I just briefly mentioned just now, the last slightly visible part of the eye will be the lens right here, which is, again, like your real camera. It sits right behind the iris and is a slightly yellow rubbery lens that functions to receive light rays and focuses them to the focal point, the focal spot on the retina. The lens is about the size of an M&M, and just like the cornea, it has no blood vessels and is composed of 2,200 fine layers. Tiny muscles around it allow for the lens to contract or expand, right here, allowing us to adjust our focus. This is also one of the key parts of the eye that will fail with age and will harden or lose some of its power to focus properly. Now, there's only 3 more parts that I want to talk about. One of them being the vitreous humor, which is right here. So it's found right inside of the eye. And like I said before, it's a kind of like a gel-like substance and allows for the eye to maintain its round ball shape, kind of like a water balloon. So unlike a camera lens, the eyes are not empty. I don't know if you've ever noticed those weird like dust-like particles floating in your eyes. Let's say when you look at a really white wall or like a really bright surface. Those are usually red blood cells and other particles called floaters, and they simply break up over time as you age, and they just float about in your vitreous humor. So that's where those would be. Now, the next one I want to talk about is a big one. It's the retina. It's likely one of the most important part of the eyes. It's a sensory tissue that lines the back of the eye that contains photoreceptors called rods and cones that convert light rays into electrical impulses. Again, taking the comparison of the camera, this would be like the digital sensor in the back of the camera behind the lens. The retina contains 125 million photoreceptors, and it lines about 85% of the back of the eyeball, as you can see here. It has about 7 million cells that are for color vision and 118 million that are for night vision. In total, the retina is about the size and thickness of a postage stamp, and it is going to be pink in color and very, very fragile. Again, like a camera lens, the image that arrives on the retina is inverted, and the brain will correct this and flip the image for us so that we can see it downside up instead of upside down. And right behind the retina is something called the choroid, and that acts as like a blotter and soaks up excess light. The last part of the eye is the optic nerve, right here. And this is going to be like the electric cable that takes all the information gathered by the retina and sends it to the brain where it can be translated into images. Light energy through neuron connections move through the optic nerve, and the optic nerve is as you can see here, a really thick rope of nerve cells on the side of each eye in the back of the eyeball. The optic nerve enters the brain through a connection known as the blind spot. So if we look at a real, at the inside of a real eye right there, you've probably seen this if you've ever had an eye exam. The optic nerve is going to be this thing here. So all the blood cells are kind of originating from this part here, and this is going to be your blind spot in your eye. Now, there's a really interesting test to actually find your own blind spot for both of your eyes, and the way to do this is actually pretty simple. So this is what we're going to do here. What you'll want to do is keep focusing on this X right here. And this is going to be, we're going to look at the blind spot for our right eye. So the way to do this is first close your left eye and stand at about 2 feet from your screen. And then slowly, while maintaining focus on here, get closer and closer and closer to the screen while keeping your eye closed, your left eye closed. And then at some point you'll see the red dot will completely disappear. And then if you get closer and closer, then it'll pop back up. And it's a really interesting thing to notice if you've never done this before. And then you can do the same thing with your other eye, and just do the reverse experiment here. So you can stop the video and try that for yourself. Now, the retina is a very complex part of the eye, so let's take a look at it into more details. The retina has 2 major regions, the peripheral and the macula. The peripheral field, where is it? So it is located on the outside edge of the eye in the peripheral field. So right here you would have the macula about within, in this circle here, where you can see the darker area. And then everything around this would be the peripheral. 85% of photoreceptors are located in the peripheral region and are very sensitive to low light. All impulses from the peripheral are funneled into one channel, making it less acute than the macular vision, which has more connections. So essentially, whatever you see that is coming from this region is less detailed than whatever is coming from this region. It is less developed and does not see color well. It is sensitive to very slight movement, and also is most useful under darkened condition. So this is kind of you can consider this as like your low light receptor for your eye. Now the macula, this thing right here in the center, this is what brings objects into focus so that the brain can analyze them properly. It represents only about 1 degree angle of coverage, so it's very, very small as far as what you can see. You can think of this as, let's say you're reading a book. What the macula can actually see and focus on at any given time is going to be about 1 to 2 to 3 letters. That's it. Everything else will seem blurry. In low light, the macula does not function really well, at least not nearly as well as the peripheral. So to see better in low light, you must move your eyes directly of the object. It's a very interesting thing to try if you've never noticed, yourself. When you're in a really dark room, the way to look at where you're going, without bumping into things, is to not look directly at the ground where you're walking, but to look come like slightly in the distance or like look away a little bit so that your peripheral vision can take over and can gather more light so that you can actually see better in low light conditions. And within the macula is a tiny yellow indentation. I don't know if you can see it here, but it's this tiny dot right here. It's very, very faint from this point of view, but it's called the fovea. Most of the color-sensitive photoreceptors, or also called cones, are located in the fovea. When focusing on a particular point, the brain automatically moves the eyes so that the visual target is in the center of the fovea. So whenever you focus on something, whenever you're looking at something and focusing on something, this portion of the eye here, this is what is going to handle that. The peripheral and the macula portions of the retina, they work together. The outside edge of the retina alerts the body that something has moved, and the brain constantly tells the muscles to move. The brain looks for change. A flash therefore gets more attention than a steady light. The peripheral is really, really good at catching movement. It's not good at discerning what it is, but it's like casting a really big net as on your entire field of vision. And then whenever there's something of interest there, it'll first spot it without really knowing what it is, and then your macula will be able to focus on it and actually discern what it is. Is it a threat, or is it something, something else? Saccades are rapid movements of the eyes that change the fixation from one point to another, and they bring the retinal image of an object of interest to lie on the fovea. So an effective layout or piece of art is often designed to move the eye from element to element, just like when reading a book, you'll look at one word after the other to form sentences and understand the meaning. You can use the same tricks when it comes to art in our ability to direct where the eye is going to look from one area of the painting to another, and then to another, and then to another, and then this way creating a story within a single image without using a single word. Now, looking at photoreceptors a little bit more, photoreceptors are found on the retina. There are two types of photoreceptors, so the rods and the cones, like I mentioned briefly. Let's start with the rods. Rods are usually found concentrated in the outer edge of the retina. So again, those are going to be found in the peripheral. And there they are. That's what they look like. On average, there are approximately 90 million rod cells in the human retina. Rod cells are more sensitive than cone cells and are almost entirely responsible for night vision. However, rods have very little role in color vision, which is one of the main reasons why colors are much less apparent in darkness. Now, cones, those are cells in the retina of the eye. Well, both of them are cells, but the cones only function in relatively bright light. There are about 6 to 7 million in the human eye, so much less, much fewer than rods, and they are concentrated in the fovea. So if we remember, most of them are found in this little area here, right in the center of the retina. These cones actually allow us to see color, detail, light intensity, changes in quick movements. There are 3 different types of cones, and they are generally referred to as long, medium, and short cones. Each of these different types are stimulated by different range of wavelength. So just like their name suggests, short cones or S receptors will allow us to perceive violet and blues when they are stimulated, whereas the L receptors, or the long cones, will allow us to perceive longer wavelength when stimulated, which we know by now result in our ability to see colors like red, for example. These 3 types of cones and their ability to capture different wavelength gives us what is called trichromatic vision. And now finally, when it comes to seeing, the brain is an extremely complicated part of the body to understand, but a simple way that I like to think of the process of seeing is the retina will act as the net to gather as much information as possible, and then will then pass it to the optic nerve, which will then send all that data to the brain for analysis. Next, the brain will translate all that electrical data into images, and from there, our understanding and our visual process will dictate how those images are stored in our memory. It's a very simplistic way to look at it, but hopefully it should help your understanding of the biological process, allowing us to see images. There's much more to cover when it comes to visual communication, but that will be for another time. This is going to conclude this first class on visual communication.